Welcome to Signal Ahead. I'm Alfred. Today's briefing, Theory and Foundations, Physics plus Math. Thursday, August 20. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. There's a temptation, when you read the science headlines, to think that theoretical physics and pure mathematics are two separate countries, that one is about the world and the other is about ideas, and that the traffic between them is occasional, ceremonial, a matter of physicists borrowing a tool now and again from the mathematician's hardware shop. I want to begin by suggesting that this picture is precisely backwards, and that if you look at what people in these fields are actually doing this month, not the press release version, the working version, you find something rather startling. The most productive thing happening at the frontier is not discovery in the ordinary sense. It is translation. The field's deepest progress right now comes from noticing that two problems, which arose in utterly different rooms of the house, are secretly the same problem wearing different clothes. Let me make that concrete, because it is easy to say and harder to feel. Consider the question of why phase transitions happen in isolated quantum systems, a genuinely hard puzzle. Because the usual story of phase transitions depends on a system being large and connected to a heat bath. And an isolated quantum system is neither of those things in the tidy way the textbook wants. Now, there is an old and beautiful idea in statistical mechanics, the Li-Yang paradigm, which says that a phase transition is really the moment when the zeros of a partition function, a purely mathematical object, a polynomial's roots wandering about in the complex plane, pinch down onto the real axis. What has been shown, and shown in more than one place at once, is that the signature of thermalization in a certain class of quantum field theories can be rewritten as the partition function of an imaginary gas of instantons, and that the notorious forbidden singularity that appears in these correlation functions is nothing other than a Li-Yang zero arriving at the real axis. The correspondence that makes this possible relates the eigenstate structure of a conformal field theory to the counting of instantons in a supersymmetric gauge theory. So a question about heat becomes a question about roots, becomes a question about instant gases. 3 languages, 1 sentence. This is the state of the field, and it is worth sitting with how peculiar it is. The value being created is not primarily new facts. It is the discovery of dictionaries. Holography, the idea that a gravitational theory in some number of dimensions is secretly equivalent to a field theory living on its boundary, is the grandest such dictionary. And you can watch people mining it right now for things like the confinement temperature of a quark-gluon plasma. And here is a lovely wrinkle that a casual reader would sail right past. It turns out that whether that confinement temperature goes up or down when you spin the plasma depends on which observer you ask. A static observer and a co-rotating observer measure opposite behavior, and, this is the point, both are correct. The disagreement between lattice calculations and holographic models dissolved not when someone found an error, but when someone realized the two camps were standing in different reference frames. Again, not a discovery of fact, but a reconciliation of translations. Now hold that thought against what is happening in mathematics proper, because the same texture appears there. When a difficult conjecture about the critical points of polynomials, where the zeros of a polynomial force the zeros of its derivative to lurk nearby, finally yields, the interesting work afterward is the work of digestion. Taking a proof that exists and making it comprehensible, reorganizing it until the load-bearing idea stands clear of the scaffolding. That is the same instinct as finding the reference frame that reconciles the plasma calculations. The frontier is increasingly a frontier of understanding what we already have. And this is exactly why a certain anxiety has entered the conversation, the worry, voiced by serious people, that this may be among the last years of mathematics and theoretical computer science, conducted in the style we have known, because machines are now beginning to do the translation. If the real work is finding the hidden sameness between two problems, and a system can be trained to hunt for hidden sameness, then the very thing that makes this a golden age of connection is the thing that might dissolve the profession that produces it. I don't think that's this year's story, and I'll tell you why later. But the anxiety is honest, and it points at something true about where we stand. So here is the argument I want to build across our time together. First, that the deep structure of physics and mathematics is now a web of correspondences rather than a stack of discoveries, and that this changes what progress even means. Second, that these dictionaries are not free. They hide their own reference frame problems, their own obstructions, their own places where the inverse map simply does not exist. And third, that the question of who or what does the translating is about to become the central question of the field. Let us begin with the web itself. There's a moment, if you spend enough time reading across the theoretical sciences, when the individual papers stop looking like separate achievements and start looking like soundings. The way sailors once dropped weighted lines to feel the shape of a sea floor they couldn't see. Each measurement is local, particular, almost trivial on its own, but taken together they trace a contour. And the contour I want to describe today is this. Across mathematics and physics, quite independently, people keep discovering that structure they assumed was contingent turns out to be forced, that what looked like an accident is actually universal. This is the deep current beneath the noise. Let me start with something small and stubborn. There's an old conjecture about polynomials. The claim that if all the roots of a polynomial sit inside the unit disk, then near every root you'll find a critical point, a place where the derivative vanishes, no further than a unit distance away. It sounds like the sort of thing that ought to be either obviously true or obviously false. It was neither. It resisted for decades, and when a proof finally arrived, the interesting thing was not that it worked, but how it worked, by treating the roots almost as a physical distribution, a cloud of charges, and asking what the geometry of that cloud is compelled to do. The result isn't a clever trick that happens to close the gap. It's a statement that the relationship between roots and critical points was never free to be otherwise. There's a rigidity there, hiding under an innocuous-looking inequality. Now hold that thought, rigidity, the sense of being forced, and turn to something that appears entirely unrelated. Consider the problem of why matter comes in 3 generations, 3 copies of the quarks and leptons, identical in every respect except their mass, their coupling to the Higgs. Nobody knows why there are 3. It could have been 1. It could have been 17. And there is a long tradition of hoping that some beautiful mathematical structure, an exceptional Lie group say, might make 3, not a fact we observe, but a consequence we derive. That the number falls out of the symmetry rather than being penciled in by hand. Whether that particular hope pans out is beside my point. The point is the shape of the yearning. It's the same yearning as in the polynomial problem, the wish, and increasingly the discovery, that what seems arbitrary is in fact compelled. And once you're tuned to this frequency, you hear it everywhere. Take the physics of confinement, the way quarks refuse to be pulled apart, the transition between the confined phase and the hot deconfined plasma. Ordinarily, this depends on grubby details, the precise shape of some potential you feed into the model. But there's a way of studying it by pretending space has many more dimensions than it does, and then expanding in the inverse of that dimension number. And when you do, something remarkable happens. The details wash out. A predictive structure emerges that doesn't care about the fine print. The authors use the word that keeps recurring in all of this: universality. The behavior near the horizon of the relevant black object organizes itself independently of what you thought were the essential inputs. That word, universality, is really the name of the current I'm tracing. It's the discovery that vast classes of different systems, built from different ingredients, converge on the same statistical fingerprint. The canonical example lives in the spectra of large random matrices. the way the spacings between eigenvalues follow patterns that don't depend on where the matrix came from. And here is where it gets genuinely eerie. There's work showing that this fingerprint survives being put through a nonlinear meat grinder. You take a spectrum, you reconstruct an operator from it by an inverse procedure, and you'd expect the delicate universal signature to be destroyed. It isn't. It reappears, transmuted, in the geometry of the reconstructed object. The universality is not a surface feature. It's woven so deep into the structure that you cannot scrub it out. So what unites the forced polynomial, the hoped-for 3 generations, the detail-blind confinement transition, and the indestructible spectral statistics? It is a single conviction, arrived at from 4 directions at once, that beneath the apparent freedom of nature and mathematics to be anything at all, there are constraints that permit far less variety than we imagined. The deep current is a current toward necessity. We spend our early education learning that things could be otherwise, that parameters are dials, that models are choices. And the mature science keeps finding that the dials are welded, that the choices were illusions, that when you push hard enough on almost any structure, it snaps back to one of a small number of universal shapes. This matters beyond aesthetics. If the world is more rigid than it looks, then understanding is possible in a way it wouldn't otherwise be, because you don't need to know everything to predict something. You need only know which universality class you're in. That, I think, is the quiet promise humming underneath every one of these papers, and it's where we'll pick up next. There is a mood that hangs over the whole of this collection, and I want to name it before we close, because it is the second-order implication that matters most. It is the tension between digestion and generation, between the labor of understanding a thing that already exists and the labor of bringing something into existence that did not. Consider what it means to digest a proof. When a mathematician takes a completed argument, say, the resolution of a long-standing conjecture about where the critical points of a polynomial must lie relative to its roots, or the careful anatomy of a counterexample that shows some appealing time-frequency structure fails to hold, and rewrites it, reorganizes it, exposes its load-bearing beams, this is not idle. Digestion is where a result stops being a rumor and becomes a possession of the community. It is how the tacit becomes teachable. And it is precisely this act, the slow chewing over, the reconstruction of an argument in one's own idiom until it is truly understood, that some now fear is entering its final season as a human craft. The worry is not that machines will fail at mathematics. The worry is that they will succeed, and that the human relationship to understanding will be quietly rerouted around us. So watch this closely, because I think the more interesting truth is being obscured by the drama of the announcement. Watch whether digestion survives, even if generation is automated, because these are different goods. A machine that produces a valid proof has not thereby produced comprehension. Comprehension lives in a mind, and the question of whether we still bother to install it there is a choice, not a fate. The corpus in front of us is, in a quiet way, an argument for why we should. Look at how many of these papers are acts of reframing rather than discovery in the raw. Someone shows that 2 research communities were arguing past each other about the confinement temperature of a rotating plasma, and that both were correct. They had simply chosen different reference frames. Someone else demonstrates that the signature of a deep universality in random matrices survives a nonlinear reconstruction and reappears, unexpectedly, in the geometry of the recovered operator. Someone maps the eigenstate thermalization of a strongly coupled field theory onto the partition function of an imaginary gas of instantons, and finds that a phase transition in one language is the famous Li-Yang migration of zeros to the real axis in the other. None of these is a brute new fact. Each is a translation, a claim that the thing you thought you understood is secretly the thing over there that you already understood better. This is what physics and mathematics actually do most of the time. They are not primarily in the business of accumulation, They are in the business of unification. And unification is a peculiarly human hunger. The reason it matters whether there are 3 generations of quarks and leptons, whether some exceptional symmetry structure could quietly explain the number 3, rather than leaving it as an unmotivated fact of the world, is not that the answer changes any prediction. It is that we cannot bear a coincidence. We do not understand. That itch is the engine. So here is the second-order implication and the thing to watch. If the generation of proofs becomes cheap, then the scarce and valuable act becomes the choice of what to unify. The taste that says these 2 problems are secretly the same. 1. This frame dissolves that disagreement. This symmetry might explain that number. A large dimension expansion that reveals a universal structure in confinement transitions, independent of the messy details of the potential, is not a computation you stumble into. It is a bet about where universality hides. The machinery that finds the answer is downstream of the human who suspected the answer was findable. And watch, too, for the failure mode. The danger of automated generation is not error. It is fluent, confident answers with no digestible interior, proofs that are correct and opaque, results with no story you could tell, a graduate student on a walk. A field that stops digesting is a field that stops being able to see the next analogy, because analogy requires a compressed, human-held model of what you already know. The obstruction papers here are instructive. The demonstration that certain curvature-dependent transformations admit no finite derivative inverse, that recovering the original object demands a differential constraint you cannot escape. Some things resist localization. Some knowledge cannot be handed to you in a closed form. It must be reconstructed with data specified, branch by branch. Understanding may be like that. What I would watch, then, over the next years, is not the leaderboard of solved problems. It is whether we keep writing the digestions, whether the human practice of chewing a result until it yields its structure survives the arrival of tools that no longer strictly require it. That practice is not nostalgia. It is where taste is trained, where the next unification is quietly incubated. Lose the generation, and you lose labor. Lose the digestion, and you lose the mind that knew what was worth generating. That is the distinction worth holding on to. Everything else, I suspect, is milestones. That's the signal for today. The noise will keep coming. We'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.